All right, so today what we're looking at is absolute dating by radioactive decay. So earlier in this unit, we looked at relative dating. That's when you just put things in order of when they happen. You determine the sequence of events, like you might say, limestone layer formed first, then sedimentary rock, or then shale layer formed second. Then there was a fold. Then there was a fault. But we didn't actually put any number values to how many years ago that was. Absolute dating is when you find out exactly how old something is in years. And the method that geologists use to absolute date things is by using radioactive decay to do so. So we're going to look at, on the notes that we're going to be going over today, what we're going to be looking at is, first off, what is radioactive decay, what half-lives are, and how it's used to figure out the age of stuff. All right, so first off, rocks contain nuclei that undergo radioactive decay. So in other words, there are atoms in the rocks, and some of these atoms, basically, they're not stable. All right, they're not stable. They're basically not happy being what they are. And as time goes by, they change into a new stable atom. So the example I'm going to use is carbon-14. Now there's different types of carbon. Carbon-14 is just one of the types of carbon. Carbon-14 is not stable. It's not happy with being what it is. As time goes by, it turns into nitrogen-14 or N14. All right. Now, there's a whole bunch of radioactive material, stuff that disintegrates into something else, but we're only going to focus on a few of them. And the example I'm going to use for most of the time is the carbon-14 example. All right, so radioactive decay happens at a predictable rate. So what that means is we know the speed at which this stuff turns into that stuff. All right, it's predictable, it's been the same. We know exactly how fast it's traveling, or how fast that change takes place. All right. Which atom will decay next is a random event. All right, so what's happening is one by one, these carbon atoms are turning into nitrogen atoms. Now we know after a certain amount of time how many of those atoms should change, but we don't know which atoms are the ones that are going to change. So the example I like to use is, let's say I had 100 pennies and I had a cookie sheet and I laid out my 100 pennies heads up on the cookie sheet, all right? Then I take my cookie sheet and I throw the pennies up in the air like that. I throw the pennies up in the air and they land. Now, I can make a pretty good guess as to how many of those pennies are going to be heads and how many of those pennies are going to be tails, because it should be around 50 heads and then 50 tails. But when I'm looking at my cookie tray to begin with, I can't point at the pennies and tell you which penny is going to be heads and which penny is going to be tails. I just know that when I throw all those pennies up in the air and they land, that half of them should be heads and half of them should be tails. It's kind of the same idea here. I know how many atoms will change, but particularly which atom is going to change, I don't know. All right. Nothing can be done to change the decay rate. All right, so the speed at which this stuff changes or decays into that stuff is a constant. It doesn't matter if I heat it up, if I cool it down, if I smash it with a hammer, if I change the air pressure, if I get it wet, it doesn't matter. That decay rate stays the same. So nothing can be done to change the decay rate. All right. Now, how we describe how fast these atoms change is we describe their half-life. So the half-life is defined as how long it takes for 1/2 of the radioactive atoms to change. All right, so so if I had 100 of the carbon-14 atoms, the half-life is how long it would take for 50 of those to turn into nitrogen. All right. Now, in your reference tables, on the very front page of your reference tables right here is the chart that shows you the half-lives of a bunch of these radioactive isotopes, atoms. So, carbon-14, the one that we were talking about so far, the disintegration or decay shows you what it turns into. So carbon-14 turns into nitrogen-14. Some of the other ones we use in this class, potassium-40, as time goes by, it disintegrates or decays into either argon-40 or calcium-40. Uranium-238, as time goes by, it turns into Pb-206, which is lead-206. And then down here, rubidium-87, or Rb-87, as time goes by, it turns into Sr-87, which is strontium-87. Now, there's a lot more than this. These are just the 4 that we use for this class. Now, over here, it shows you what the half-life is, which again is the time it takes for 1/2 of the material to change. So 1/2 of this stuff to change into that stuff, this is how much time. And you can see the half-lives vary quite a bit. So for carbon-14, 5.7 times 10 to the 3, that's 5,700 years. For potassium-40, 1.3 times 10 to the 9, that's 1.3 billion years. For uranium-238, 4.5 times 10 to the 9, that's 4.5 billion years. And then rubidium-87, 4.9 times 10 to the 10, that's 49 billion years. That has a really, really long half-life. All right. All right. So how we know which one of those radioactive isotopes we're going to use to date a rock depends on what we're trying to date. And the analogy I like to use is, let's say you're trying to find the length of something. All right, what tool you're going to use to measure the length of something depends on, roughly what the length of it is. So, for example, a ruler, a meter stick, a tape measure, and the odometer on your car all measure distances. All right, but if I'm going to try to measure the width of a school desk, I'm not going to use the odometer in a car to do that. Nor if I'm trying to measure the distance between Syracuse or Rochester, I'm not going to use a ruler to do that. So I have to pick the right tool based on what the approximate thing I'm trying to measure. So kind of the same thing here. If there's something that I suspect is in the thousands of years old, I would want to use something that has a half-life in the thousands of years to find the age of it. If there's some rocks that I suspect to be 500 million years old, then I'd probably want to use something with a half-life in the hundreds of millions or billions of years to do that. So that's one of the criteria for choosing which one of these radioactive isotopes I want to use to find the age of it. Another thing is carbon-14 is found in organic remains. So usually carbon-14 is used to find the age of things like bones or wood, things that are one-time living. So if I was researching an area in ancient Rome, or if I was researching an area in Rome and I find some ancient remains of a wooden bowl that I suspected belonged to some ancient Roman senator, that's going to be in thousands of years old. So I'd use carbon-14 for that. If I found some rock, some igneous rock that I suspected to be 500 million years old, then I might use one of these guys right here. All right. Now, and how you go about doing that, we'll look at in a minute. All right. Age can be found from the relative amounts of undecayed substance and decay constant. So I'll show you how to do that in a minute. Now, using radioactive decay to find the age of rocks has its limitations. Right? And a few of the limitations are, it really only works well on igneous rocks and organic remains. Right? It works well in igneous rocks because there's a set birthday of an igneous rock. You know, when the lava cools and hardens into a rock, that's like the birth date of the rock. That's the age you're going to get when you find the age of the rock. Or living things, all right? Same kind of idea there. There's a set date you can go back to. It does not work at all really on sedimentary rocks. And the reason for that is because sedimentary rocks are made from little pieces that are stuck together. All those pieces could come from different places. And they can be from different ages. So I might have, if I have a piece of conglomerate, one pebble might be 1 billion years old, another pebble might be 1 million years old, another pebble might be 100,000 years old. And so getting an age of all those things would just be kind of like a hodgepodge of all those things mixed together, which wouldn't mean anything. So it does not work on sedimentary rocks, and that's a shame because the Earth's surface is mostly made out of sedimentary rocks. And it doesn't work really very well on metamorphic rocks either. And the reason being is metamorphism is more of a gradual process. So like when sandstone turns into quartzite, it's gradually the heat and pressure kind of makes it change from one to the other. It's really hard to pinpoint an exact moment when it like flips a switch from one to the next. So it doesn't really work too well on metamorphic rocks, doesn't really work at all on sedimentary rocks. So you're really limited to the igneous rocks and organic remains for this. All right. Now, how do you go about doing this? All right. Well, I'll use carbon-14 as an example. It's just the easiest one to use. So if I have a sample that is, I measure it and it's 100% carbon-14, that means that sample has undergone 0 half-lives. And that is basically 0 years old. If I have a sample and I analyze it and it is half carbon-14 and half nitrogen-14, what that means is it has undergone 1, and I'll just abbreviate HL. It's undergone 1 half-life. And just a few minutes ago, we looked up in the reference tables, and the half-life of carbon-14 was 5,700 years. So if I had half nitrogen and half carbon, it's undergone 1 half-life, and 1 half-life according to the reference tables for carbon-14, 5,700 years. Right. Let's say I had a sample, I analyzed it, and it was 1/4 carbon and 3/4 nitrogen. All right. In that case, that has gone through 2 half-lives. Because a quarter is a half of a half. All right. So here I chop that in half. Here I chop that in half. So if I have a quarter left, I've gone through 2 half-lives. Now each half-life is 5,700 years. So it's going to be 2 times 5,700, which is 11,400 years. Okay. If I have a sample that has that much carbon and that much nitrogen, all right, so an eighth is a half of a quarter, right? So that means I've gone through another half-life, so 3 half-lives, right? Again, each half-life is 5,700, so 3 times 5,700 is 17,100 years old, right? And, if I would have a 16th, next one would be 4 half-lives, and then 4 times 5,700, and so forth and so forth. Now, you can see one of the things that why I can't date something that's like millions of years old with carbon-14 is what's going to happen is, for carbon-14, it usually kind of ends at about 50,000. And the reason being is because this keeps getting smaller and smaller and smaller and smaller, and it gets harder to measure. So usually things under 50,000 years old are what you can date with carbon-14. All right. So one way to express this is like using charts like this. Another way this radioactive dating stuff is sometimes expressed is in the form of a graph like this. So if I have the number of half-lives down there and the percent remaining right here, If I was going to plot my carbon-14, I'd start off, I had 100% carbon-14 at 0 half-lives. Okay? At 1 half-life, I had 50% carbon-14. At 2 half-lives, I had 25% carbon-14. At 3 half-lives, I had about 12.5% carbon-14. Right. The next one, half of 12, would be about 6. So it'd be like that. And then half of 6, the next one, half of 6 would be 3. So my graph for what happens to the amount of carbon-14 is not a straight graph down, it's a curving graph down. Right. So let's say I had a sample that had, I analyzed it and it had, let's say 40% carbon-14, right? What I could do is I could look up 40 right there, then come over here and then come down, and I might say it took 1.4 half-lives, and then I would do 1.4 times 5,700, and that would give me the age. All right. So that's what's happened to the amount of carbon-14. If I was going to plot what's happened to the amount of nitrogen, well, I start off with 0 nitrogen, so I'm down there. After 1 half-life, I have 50% nitrogen. All right. After 2 half-lives, I have 75% nitrogen. After 3 half-lives, I have about 88% nitrogen. Oops. 4 half-lives would be like 93, then 96. So the amount of nitrogen I have is getting closer and closer and closer to 100. The amount of carbon is getting closer and closer and closer to 0. The amount of nitrogen is getting closer and closer and closer to 100. So as the carbon's going down, the amount of carbon I have is going down. The amount of nitrogen I have is going up. So if I plotted, again, I've used carbon-14 as most of my examples, but if I plotted the uranium-238 and lead-206, it would look like that too. All right. So that's just another way to show the radioactive dating data. All right. So that's how you do the process. That's how you figure out the absolute ages of things by radioactive dating. You measure how much of the original stuff, how much of it, what it turns into. So you measure how much, what we call parent material, and you measure how much of the daughter material turned into, and then you can figure out how many half-lives it's gone through, and then multiply that by how long half-life is, which is in your reference tables, and then you can figure out the age of it. All right, so that is radioactive dating.